Right, okay, so the quicksort process, it is a mega algorithm. It doesn't really sort in the same way that merge sort doesn't. It doesn't say, right, how do we sort all these numbers? It says, no. How do we partially sort these numbers? And if we keep partially sorting until we get down to single items, then we're good to go. So let's just do, I won't do too many because it gets quite long-winded. They'll tend to ask you to do a pass. Okay, so let me have some numbers. So 10, 17, 5, 9, 12, 20. Yeah, that'll do me. No, I'll do one more. Let's have 14. Right, okay, so we're going to quick sort these numbers. The start of quick sort is to set up a left pointer, a right pointer, and a pivot. Now, it's actually quite nice to visualize because the left and right pointers move in. The only bad bit is when you do the swaps. But you should never have to put more than 3 numbers together. So if you leave enough space around your numbers, you should be able to do this. Right, so we start by quick sorting the entire list. Okay? The goal is to pick a value, and in this case we just sit it at the left hand side. And we want, by the time we finish this pass, for everything smaller to the 10 to be on its left, and everything larger than the 10 to be on the right. Okay, so you looking at that, you can see there are a couple of numbers that will be on the left. The majority of the numbers are going to be on the right. Okay, doesn't work with duplicate numbers. Most of the sort of things throw a fit in that way. But generally we're sorting key values, so you shouldn't have duplicates anyway. Okay, right.
If you did throw it at something that was the same, how would it treat it?
It gets complicated. How many are going to be the same? If you've got 2, you could probably handle that. Once it starts getting to an undetermined number of duplicates. If all you're interested is purely putting something in ascending or descending order, and there's no other relationship to anything, it wouldn't matter, would it?
If you're sorting references or something like that, and you just get something referencing the same, that would screw everything up.
Yeah, if they're generally they're key values, so they are going to be unique. Right. Okay. So the general process is compare the items at the left and right. If they're in the correct order, and we'll go ascending on this. If they're in the correct order, don't move anything, and we adjust the pointers, and we just keep doing that until the left and right pointers are in the same position. Okay. Which means we've located the place the pivot lives. And we then have got a problem of, we've got 2 lists to sort. Let's quick sort each of those 2 lists. Remember we said this is highly parallelable because there's no interaction between the 2 parts of the list. But let's go through this. So we've got 10 and 14. If we're going ascending, then they are in the right order. So the process is, the pointer that isn't associated with the pivot moves in. So our right pointer is going to move in. We then compare the numbers at the left and right pointers. 10 and 20, they're relatively in the right order. So we move in the pointer not associated with the pivot. So the right one moves again. Okay. So I am showing the pointers moving. That's what I've got to try and demonstrate here. Right. So you could, if you wanted to comment it, do the commentary. Just say what 2 numbers you're looking at. So you could say 10 and 14. No, they're in the right order. Moving right. 10 and 20. Right order. Moving right. Just do that if you want to write it as a commentary. Okay. So we've got 10 and 12. Again, they're relatively in the right order. So we're going to move the pointer not with the pivot. Now we get our first bit of work that it's got to do. So this has been a quick process so far because all we're doing is decrementing a pointer. We've got to do an if, we've got to do a compare, but we're decrementing a pointer, so it's quick. Right, now we get our first issue. 10 and 9 are not in the right order. So what we've got to do is swap them. The key thing you've got to do is the pivot's got to stay with the 10. Okay, so I'm going to move the 10 there. So I'm going to cross through. I'm not going to scribble. I'm going to cross out and put a 10. I'm going to move my pivot to there. So I'm going to cross out the pivot there, but I'm going to do it by just putting a marker under it. I've got to put my 9 where the 10 was. So I'm going to cross through and put my 9. So I've now swapped the two values, the 9 and the 10. My pivot has moved. That's the key thing. So my pivot has stayed with the 10. I've finished my moving about. I now move in the pointer not associated with the pivot. So we can see that the left pointer is no longer with the pivot. That one moves in. Yeah? So the left pointer goes across. Now, this is one of the things that gets quicksort a little bit. A little bit of movement going on, so we're going to end up swapping back here. 10 and 17, they're not in the correct order, are they? So we're going to swap. So we're going to move the 10 there, so we're going to cross through that. Going to put a 10. The pivot needs to move. So the X's are showing when I have to do a swap as well. So it's like a backup explanation. I need to put my 17 where the 10 was. So this is the maximum number of crossing outs you'll have to do. So that's now going to be 17. So I'm going to put that there. I'm now going to move in the pointer not associated with the pivot. So the R, the right pointer, is not associated with the pivot. So that moves in. We're getting close. We're getting close. The process again, compare the left and right values. Don't compare the left and right pointers, because that'd be stupid, because they're pointers. The values at the pointers. Right, 10 and 5. Not in the right position, we've got to swap them again. Merge doesn't do all this swapping around. That's why it kicks it. So, we cross through, we put our 10, cross through, put our 5. So as long as you leave space to be able to write 3 numbers, you're alright to do this. Okay. Right, the pivot's moved, so we need to just mark it so it's no longer there. It's now associated with the right pointer, because that's where the 10 is. We now move in the pointer not associated with the pivot, which is the left pointer. So the left pointer moves in, ends up there, end of quicksort partition.
Left equals right.
Yeah. So as soon as the left is, which is a little bit, how you put the logic of that in your algorithm, you could do a less than if you wanted to. I think I do on mine. But essentially, that is our stock condition. When the pointers are in the same position, and we can do a double check to make sure we haven't screwed it up. There's the 10. You can see where the 10 is because that's where the pivot is. These were the historical positions. So it's actually moved 3 times. But to the right of it is 17, 12, 20, 14. They're all bigger. They're not in order, notice. They're still a jumble. But as a bucket, they are all bigger. To the left of it is 5 and 9. So that is the end of that phase. What we would then do is say, well, actually, now we've got 2 problems. We've got 2 lists that are not sorted. But we would apply quicksort. So if we were using numbers for the indexes, so if I better start at that one. So that's 0, 1, 2, 3, 4, 5, and 6. When we initially initiated the quicksort, we did this. We did quicksort, and we just give the upper and lower bounds. So we'd say 0, 6. We've now degenerated the problem. Can you see that the 10's actually in the right place in the list? That's the interesting bit. So the pivot, bang, it's in the right spot. We then need to quicksort positions 0 to 1, and we also need to quicksort. So we're tackling the list to the left of the pivot and to the right of the pivot. So that's going to be 3, 6. So this is 0, pivot minus 1. This is pivot plus 1 to the end. the original position of the left pointer, the original position of the right pointer when it started. So we're at 0 and 6. And obviously, if you then want to demonstrate that again. Now this one's interesting. You could quicksort it. But actually, if you've got two numbers, it's easier to just do a comparison, isn't it? Just say, oh, that one's small and that, move them if they need to be. Don't do a full quicksort. No point. This one, yeah, a little bit more work to do. But if you look at where the data is, so you've got a 17 there. So when we initiate the quicksort for that one, that's going to be our pivot value. So the 17, I can see this just by looking, would end up there. The 20 should go there. The 12 and 14, it's difficult to predict what order they're going to be in. So don't second guess. Don't try and guess where everything is. The process is what matters. And that's all quicksort does. So to implement it, it's not that hard to implement. It's a lot easier to implement than merge sort. I quite like quicksort. I've always liked quicksort. I think it's just clever. Because it isn't actually sorting anything. It's just dumping stuff to the left and right. It's bin sorting nearly. It's just saying like, oh, you're all smaller, you go over there. If there was another way of working out what was the larger and smaller ones, there'd be another sorting method there. I think that's what a lot of the radix sorts do anyway. They don't try and sort. Whereas if you look at bubble sort was trying to sort all the numbers. Insertion sort is trying to sort all the numbers. This one, it's not. It's just saying I'm just going to keep moving stuff around. Merge sort doesn't even care, does it? Just because I'm just going to take things and merge them together. Anyone got any questions about that?
You recorded all that, didn't you?
I think I did. Yeah. Let me do the 3-6 just to carry on. I'm going to draw it out.
Why did you do 3, 6 and 0?
Because the pivot's at position 2. And the pivot's now nailed in position.
So that's the final...
That's the final place. If you look at it,
So
there are two numbers smaller than 10.
Right,
so 10 must logically be in the right place.
So that's the next line for the next lot of sorting.
Yeah.
Yeah.
So we've got time. I'll do this one if the wind had quietened down a bit. Right. So all I'm going to do, I'm just going to, and you can see it's two isolated lists. So these can be worked on independently in parallel. So I have got now 17, 12, 20 and 14. And I'm going to quicksort those. So I'm going to put my left pointer there and my pivot. I'm going to put my right pointer there. Picking the pivot, you can do loads of weird things, but statistically it really doesn't matter. Where you pick, you can pick any number to be the pivot. Doesn't matter. Right, so the left and right pointers. We're looking to see, are the values in the correct order? They're not. So we're going to move the 17 to there. We're going to put the pivot over there, so the pivot's gone. We're going to put the 14 where the 17 was. We're going to move in the pointer not associated with the pivot, which is now the left pointer. And then we're going to start our comparison loop again. So we look at 12 and 17. Aha, that's good. 12 and 17 are relatively in the right position. So we move in the pointer not associated with the pivot. Oh, days, the building has come down. Right, so we've moved in. We've got our last comparison to do here. They're not in the right order. So we're going to swap them over. So the 17 goes where the 20 was, and the 20 goes where the 17. The pivot has moved. And it's important that you don't lose track of where the pivot is, because if you move the wrong pointer in, you'll break it. Right, so we've moved the pivot. So the one not associated is the right pointer. So that moves in. Stop. Okay, so that then generates a quicksort from 3 to 4, and a quicksort of, what am I writing 20 down for? 6, 6. Which is our stock condition for the 1962 version of quicksort when it was first come up with. But again, you can see in short order we got down to things that were trivials. Obviously that's very trivial because that is definitely in order. So actually you could put something in there that didn't even bother calling. Remember, there's a cost. Whenever we call a function, there's a cost. Time to put things on the stack, time to take things off the stack. And when you're doing something millions of times, that cost can actually start, I don't know, you found that, didn't you, when you did the iterative one?
Yeah.
It does make a difference. It's incredible, really. Even though you've still got to maintain a stack somehow. The function calling does cost. Which is why in C you can define a function in C and tell the compiler to inline it. So it doesn't do a function call, it just takes the code from the function and says, dumps it in your code at that point.
That must make a lot of...
It makes some horrible code, but it means
say.
you can keep your source code nice and clean. You're letting the compiler do the dirty work.
That must be like...
Inlining, they call it. It's good. It's what you do when you're doing assembly language programming. You'll start with subroutines, and then you go, I want a bit more speed, sod it. And I want it to run 100 times. Let's just copy the code 100 times. So you can get rid of any loops as well, because that costs. Doing a comparison, say, has the loop finished yet? If you know it's going to run 100 times, if you can calculate that you want it to run 70 times, you can jump halfway down the code to start, so the code runs 70 times.
Okay, so instead of doing the comparisons, you just have it set.
Oh yeah.
If you know your maximum you're going to run it is 100.